Okay, welcome to the sub-project about the convolutional beamformer. My name is Christoph Bödecke and I will present the first part, and Wang Yu will later take over and present the second part. Okay, let me first start with the motivation and the scenarios that we consider. We assume we have multiple talkers and also some noise that is recorded from multiple microphones, and also we capture some reverberation, and we want to separate the speakers, suppress the noise, and eliminate the reverberation. And to do this, we want to do it with a convolutional beamformer. This is a maximum likelihood beamformer that can do simultaneously reverberation, denoising, and source extraction, and is jointly optimal. And it has shown that it outperforms the classical approach of WPE for reverberation, followed by beamforming. And furthermore, this beamformer can be factorized in a reverberation component that is WPE, followed by a special beamformer. But here we then have a feedback between beamforming and reverberation. And what we actually plan to do with it is that we use a neural network to support this convolutional beamformer and have an objective after the beamformer. So we are doing an end-to-end optimization of the neural network for the beamforming. For that, we use the neural network to estimate statistics for WPE and also to estimate statistics for the beamformer, as it was done in earlier work, and also in joint optimization was already done. But here we want to change a few things. So we want to estimate the relative transfer function on a dereverberated signal with spatial whitening instead of using column selection mode. Furthermore, we want to replace the eigenvalue decomposition with power iteration. Let me now explain the overview of the system. So we have a multi-channel input signal to the neural network, and this neural network then estimates some time frequency statistics for the beamformer, and then the beamformer has the task to extract the desired speaker given the multi-channel observation. This estimated speech then can be forwarded to an ASR system that tries to predict the transcription. Now let me explain the extraction part a little more in detail. The classical approach is visualized in the first figure. So first we have the multi-channel observation, then we dereverberate the signal with WPE, and then we apply an MVDR beamformer, for example. Both components are separately optimal, but not jointly optimal. And last year, the convolutional beamformer was presented that is just one block and is jointly optimal. And this year, we showed that it can be factorized in WPE and a special beamformer, the WMPDR beamformer. And here we have a feedback between the beamformer and WPE. So WPE is in this case now speaker dependent. When we now want to use the neural network to support WPE and the beamformer, the neural network estimates the masks that are used to estimate the statistics inside the beamformer, and it estimates the inverse of the clean speech power that is used inside the WPE algorithm. And we then have to backpropagate the gradient from the output of the beamformer back to the neural network through the beamforming operation and also through the WPE operation. When we now want to extend the system to multiple speakers, we have to add a second WPE block and a second beamformer block, and this extracts then the other speaker. The important point here is that WPE is speaker dependent, and the neural network has to estimate the inverse clean speech of the desired speaker. When we realized it, we wanted to do it with PyTorch, and there we encountered a few problems. First, PyTorch has no native support for complex numbers, so we used a package that mapped the operations from complex to real valued ones. And there we encountered some stability problems, but we contacted the maintainer of the repository, and he proposed an alternative implementation, and this one was much better than the previous one. Furthermore, for the relative transfer function estimation inside the beamformer, we need the eigenvalue decomposition, and there's a problem that first, the gradient is not implemented, and second, if it would be implemented, the gradient would be singular. So instead of the eigenvalue decomposition, we propose to use the power iteration that can be backpropagated. Furthermore, if you realize that you usually encounter some memory problems, because inside the WPE algorithm, there are some large intermediate values that consume several gigabytes of memory. To tackle this, you can use stride tricks or recompute trade-offs. Now let me explain a little bit more about the beamformer and how it is used in the optimization. So on the left side, you see the relative transfer function estimation, and on the right side, the beamformer that uses that estimation. And in total, we need 3 different types of covariance matrices, one for the target, so the speaker, one for the distortion, crosstalker, and noise, and one is a weighted estimation where we use the inverse of the clean speech power. And the neural network now has to estimate the masks and the inverse clean speech power. So since the eigenvalue decomposition cannot be backpropagated inside of PyTorch, we propose to use the power iteration that you can see here on the left side of the slide. And here I want to highlight one interesting point. If we just use a single iteration inside the power iteration, we obtain the equation on the left bottom of the slide. And when we now compare it with the MVDR solution from Zuden, that is very popular as an alternative beamformer, we see both beamformers are just a scaled version of the other one. So they are relatively similar. Now I have some preliminary results here. So here you can see the training curve on the LibreCSS2 mix data, and it's just the training for a single epoch. And here you see the SDR measurement while this network was training. The blue curve is a reference signal, still trained on a signal level loss, so the gradients are backpropagated through the classical pipeline. Then we replaced the WPE component with a speaker-dependent WPE component, and we actually observed a slightly degeneration in the performance. Then we replaced the beamformer with the weighted MPDR and one power iteration, and it further slightly degenerates. But if we increase the number of power iterations, we get a better result than the reference system. And now let me summarize what I presented here. It's still an ongoing research, but the training curves already indicates that the system is working. And the power iteration can be used inside the convolutional beamformer and yields some good results. Now I want to hand over to Wang Yu, who will present the joint optimization of convolutional beamformer and ASR.
Hello, everyone. I'm Wang Yu Zhang from Shanghai Jiaotong University, and I will introduce the joint optimization of a convolutional beamformer with ASR in this part. The reason why we want to tackle this topic is that, as Christoph mentioned, the convolutional beamformer has shown much stronger capability than the conventional cascade of WPE and NVIDIA beamformer, and also recently joint optimization of front-end and back-end, and also shows promising results in both single speaker and multi-speaker scenarios. So in this project, we want to explore the joint optimization of end-to-end ASR and the newly proposed convolutional beamformer, and evaluate them on both utterance level mixture and long recording like LibreCSS. And in our project, we have 2 kinds of evaluations on the common data set LibreCSS. The first one is the utterance-wise evaluation. For each long recording, they first divided into several segments based on the Oracle segmentation information, and each segment contains a complete utterance of one speaker. So we can evaluate our system on each Oracle segment. The system can be either a multi-channel speech separation and recognition system or a single-channel multi-speaker speech recognition system. And the other is a continuous speech separation pipeline. First, it divides the long recording input into many fixed length segments with a sliding window. We do speech separation for each window and generate 2 strings of separated speech. Second, the separated strings in different windows are combined together to form 2 strings of long recordings by applying a stitching algorithm. The 2 strings ideally contain complementary speakers without overlap inside. Third, we perform speech activity detection on each long string to eliminate silent regions and generate several shorter segments. Finally, these segments are fed into the ASR module for speech recognition. And in this figure, this is a basic architecture for our joint optimization with ASR. It is the published work named MIMO Speech. And as shown in this figure, it consists of 2 main modules, the front-end module for speech separation and the back-end module for speech recognition. The loss is backpropagated from the back-end to the front-end so that the model is jointly optimized. In our project, we want to extend this architecture to include dereverberation because reverberation is common in many realistic conditions, including LibreCSS, and often leads to performance degradation in speech separation and in ASR. So we have several possible extensions. The first one is the cascade of WPE and NVIDIA beamformer. It simply introduces a WPE module in front of the NVIDIA beamformer. Oh, sorry, I think I lost the control.
Yeah, I can do that. I think it's better that I can help with that. So.
Yeah. Okay. Thank you.
Yeah.
Can you go back?
Okay.
Slides earlier.
8. Yeah.
Yeah.
8.
No, it's 6.
I'm already showing the 6, I think.
Yeah.
Okay. It's a bit delay. Okay. Thank you. And yeah, this is the first architecture, which is a simple cascade of DNWP and the NVIDIA beamforming. And the next slide is the second extension of the MIMO speech, which is the factorized form of convolutional beamformer, which is WP followed by weighted MPDR beamforming, as mentioned by Christoph. And the estimated signal variance is shared among the WPE module and the weighted MPDR module. And the third extension is to use the unified form of a convolutional beamformer, also named WPD. It unifies the WPE module and the MPDR beamforming into a single convolutional beamformer. These are the 3 extended architectures for joint optimization with ASR. And in next slides, I introduce the main problems that we try to solve in this workshop. During the workshop, we have spent much time trying to solve the problems in joint optimization. One of the biggest problems is a numerical instability issue, which is a common problem that we often observe in the joint optimization with ASR. This phenomenon is that many warnings appear during training, reporting gradient is not a number. And this causes many batches to be wasted and makes it difficult for the model to converge. The cause of this problem might be, for example, some complex matrix operations in the WP and the beamforming, such as the matrix inverse, and also some numerical overflow in some operations. So we have many discussions and trials to solve this problem. And in the next slides, we have some final solutions to make this problem finally solved. First, we use a double precision for internal operations in WPE and beamforming, which was also reported critical in some previous studies. And the second, we add some regularization term to the covariance matrices in WP and beamforming, and also the estimated masks. For example, we add a constant diagonal loading to the covariance matrices and also flooring the masks with a constant, small constant. And third, we replace the matrix inverse with a solve function, which is a more accurate and stable. And we also use the updated implementation of these operations in torch complex, thanks to Naoki Camel. And these new implementations are now available in the torch complex repository, and they are more stable and accurate. With the above techniques, the numerical instability issue is greatly mitigated, and we can do the joint optimization now. In next slide, we have some preliminary experimental experiments on both simulated data and the library CSS data. And the simulated data contains both single speaker samples and multi-speaker mixtures. Here is the detailed configuration, but I won't go into details. In next slide, I introduce that we train all our models on the simulated data, including the single channel multi-speaker model, ASR model, and the individual modules of the MIMO model, and also the jointly optimized MIMO model. And in the next slide, we have the results of these models on the simulated mixture data. The first line of this table is the single channel multi-speaker ASR, which achieves 16% WER on both depth and devel set. And the MIMO model with separately trained modules achieves relatively bad results currently. There may be several reasons. First is that the front-end module is not fully well trained till now. It is still converging. And the second, there is naturally a mismatch between the front-end and back-end modules because they are separately trained and simply concatenated together for evaluation. And third, a simple combination of the separately trained modules cannot handle this single speaker samples correctly because there is energy leakage in the beamformer, and it cannot output a fully silent stream. So it will generate many insertion errors in the single speaker samples. But these problems can be mostly handled by using the joint optimization. And we can see in the last line that the jointly optimized MIMO model can achieve a great improvement performance with 10% on WER on both sets. And we also evaluate the single channel multi-speaker ASR model on the library CSS data. Here we mainly focus on the oracle segments. It is the utterance-wise evaluation. And as we can see, it achieves a great improvement in the samples of higher overlap ratios, but decrease some of the performance in samples with lower overlap ratios. This might be a common problem for the multi-speaker modules trained with permutation invariant training, and we will further investigate this model. To summarize, we introduced the convolutional beamformer and its extensions to joint optimization, and we also explored some techniques to solve the numerical instability issue in joint optimization with ASR. And in our preliminary experiments on both simulated data and the review CSS, we got some promising results on the simulated data, and we will further continue this project after the workshop. And we will finish training the jointly optimized MIMO model with the convolutional beamformer and evaluated it on the library CSS. Thank you.
Next, we have the target speaker voice activation detection from USTC by the presentation by Mo Hui, Yan Hui, and Li.